Hello, welcome to our impulse and momentum unit. This unit there is new material in this unit, but we're not going to get to we're going to get to some new stuff, but it's very much based on our forces and kinematics unit. And as a matter of fact, in order to kind of define some new terms, well, impulse and momentum, we're going to go back and think about topics or concepts or scenarios that should be very familiar to you. Let's say that you want to change the velocity of an object. You have an object, you want to change its velocity. What factors would affect how much the velocity will change given what you do to it? Okay, so think about it. What could you do to make sure that the velocity changes? Let's say you want to really make you want the velocity to change of this object by a lot. What could you do to ensure that happens? Well, I think one of the most obvious things, if we think about this in terms of forces and kinematics principles that is you could affect the net force that you put on that object. And I think you could pretty reasonably come to the conclusion that by increasing the net force, by making there be more net force, then you're going to get a bigger change in velocity. You're going to get a bigger delta V. Okay? And that makes sense. If you push on something harder, you're going to make its velocity change by more. I think that's pretty common sense. Another way that we could write this is to say that the change in velocity is proportional to the net force. Okay, and remember, delta V means V minus V naught, the change from final speed to initial speed. That's what we're looking for here. There's some other factors, though, that would influence this as well. I think one of the other common ones you might think of might be the time that the net force acts for. How long is that net force being applied? And I think this is also pretty reasonable. If you apply a net force for more time, there should be a bigger change in velocity. I think that's pretty common sense. More time leads to a bigger delta V. Another way of saying that, again, is delta V is proportional to time. The last one that I think would really affect it, or the last factor, would be the mass of the object, how much mass it has. And think about this one carefully because it doesn't work the same way. If you have the same force pushing a more massive object, it doesn't accelerate at as big a rate. Think about Newton's second law. The acceleration would be smaller for a bigger object. It's harder to get bigger objects to change their velocity. So more mass, in this case, actually leads to a smaller delta V. Now, how do we show that with a proportionality? Clearly, we can't write that delta V is proportional to m, because that would mean more mass means a bigger change in velocity, and that's not what we see. We can't just throw a negative sign on there. What we have to do is instead write it as the inverse of m. Delta V is proportional to the inverse of m, meaning as m gets bigger, delta V gets smaller. As m gets smaller, delta V gets bigger, and that's exactly how this fraction would behave. If you decrease m, you might be decreasing m, but you're increasing the fraction as a whole. It turns out that we can actually put all these factors together. And instead of writing proportionalities, we can write an equation. If V is proportional to F net and proportional to T, then that means that we can write it like this. Delta V, is equal to, notice that they're both going on top of the fraction, the net force multiplied by the time, but notice it's also proportional to 1 over m. That's going to go on the bottom of my fraction. It turns out if you want to change the velocity of an object, the amount that the velocity changes is going to be equal to the net force multiplied by the time divided by the mass. Here's a more common way to write that. I'm going to multiply both sides by m, and you end up with m times delta V equals F net times T. The mass times the change in velocity is equal to the net force on the object multiplied by the time that the net force acts for. We're going to leave this for just a minute. We're going to go define our terms, and then we're going to see how they relate back to this equation that we just came up with. Okay? We put this together just based on common sense. I shouldn't say common sense, based on results that seem to make a lot of sense that you could study and do in a lab. The first term we're going to define is momentum. This is going to sound like kind of a weird definition. Momentum is a quantity that represents an object's motion. And the reason I'm going to call it motion is because the equation for momentum is as follows. P equals m times v. That is right on your reference tables. It is right here. Those little arrows on top of the P and on top of the V just remind you that this is a vector. Okay? The reason I'm saying it represents an object's motion is because momentum is not just the same as velocity. It's not just the same as an object that moves. Well, it's not just the same as the mass. It's equal to the product of the mass and the velocity. Now, you might say, well, why do we care? Okay, why are we multiplying mass and velocity together? The short answer is because it helps us with other things that we will see later on, okay? It turns out that it's kind of like energy. It turns out that this is kind of useful for some applications. That's why we study it. It's not as obvious as, like, let's say velocity. Like, obviously want to know how fast something is going. It's not necessarily obvious that you want to know what the product of mass and velocity is right now, but I promise you it will be later on. Some people complain that the symbol for momentum is P. I like to make the joke, it's not an original, that the reason the symbol is P is because, and this is a joke, it's not really real, there's a silent P at the front of momentum, kind of like pneumonia or pneumatic. So it's really momentum, but there's a silent P. So sometimes you'll hear me talk about momentum, but it's a silent P. And just so we're clear, it doesn't actually exist. It's a joke. This is not real. Momentum is real. The P up here is not. The units for momentum are the units of mass times the units of velocity. So the units are kilograms times meters over seconds. I'm going to go right into defining impulse. Impulse is a change in an object's motion. So interestingly, we have something that represents an object's motion. Impulse is a change in an object's motion. And that change in an object's motion is caused by a net force acting over time. So here's where we're going to start to see some connections. The symbol for impulse is J. Again, a little confusing. This really stupid joke that I like to make is that there's a silent J out front, and originally it was pronounced like you would pronounce a word in Spanish that has a J out front, like impulse. That's, again, not real, but it sometimes, if people ever ask why that J is there, that's what I tell them in jest. A change in an object's motion caused by a net force acting over time. Well, net force acting over time, the impulse is equal to the product of those two things, F net times time. And would you look at that? F net times time was in our equation up here, which means that if impulse is equal to net force times time, it's also got to be equal to the mass times the change in velocity. And again, I do just want to point out one more time that this impulse is a vector, and the units are the units of net force times time, or it could also be the units of m times delta v, mass times change in velocity. Well, mass and velocity, that's units of kg times m over s. But wait a second, that's the same units as momentum, which is interesting. There's got to be some sort of relationship between momentum and impulse. Okay? Momentum is the mass times velocity. Impulse is the mass times the change in velocity. They've got the same units. They're both vectors. There's got to be some deeper relationship here. Well, if you think about it, since momentum is equal to mass times velocity, then how would we change an object's momentum? How would we find delta P? What would be the easiest way to change an object's momentum? If momentum is mass times velocity, usually we can't change the mass of an object, but we can very easily change the velocity. So if we want to change the momentum, that's got to be equal to m delta v. Again, the mass typically stays the same, but the velocity is usually very easy to change. Or at least you can change an object's velocity more simply than you can change its mass. Mass doesn't usually change. So if momentum is m times v, and the change in momentum has got to be m times delta v, look what we can do. We can take that equation from up here, J equals F net times t equals m delta v. We just got done saying that m delta v is the mass times the change in velocity. That's got to be equal to a change in momentum. So what we've done is we've linked what an impulse is to momentum. Impulse and momentum are not the same thing, but instead an impulse is equal to a change in momentum. Impulse is not equal to momentum. Instead, impulse equals a change in momentum. And that's borne out in the equation that you have right here. Okay, an impulse is equal to a change in momentum. That's really important to understand that these are not the same thing. The momentum of an object is mass times velocity. If you provide an impulse to something, you're going to change the object's momentum. Okay? Impulse can also be calculated by multiplying the net force times the time, but importantly, its relationship to momentum is that it is the change in momentum for an object after a net force is applied for some time. We'll just get right into the examples, or at least this example here. Impulse can be a little tricky. Impulse and momentum can be a little tricky if you don't follow some rules, okay? Because if you look at this, there's a lot of things that are equal to each other. My advice is always for things like this to use this equation, but pick what you need to start with. Pick what you need from the equation and solve. In other words, if you're looking for the change in momentum and you're given, like, let's say the mass and the change in velocity, and the question doesn't say anything at all about the net force and the time, don't bother writing down the net force and the time stuff. Just worry about delta P equals m delta V. Now, sometimes you might have to kind of solve for a couple different things before you get to what you really want, but don't think you always have to write this full equation out every single time. You can use different pieces since all of these expressions are equal to one another. You can use different pieces and kind of mix and match, and you'll see what I mean in just a little bit. So you pick what you need from the equation and you solve. The other thing that really messes people up if you have different measurable quantities that are in opposite directions, and it tells you that, such as there's a velocity to the east but an impulse to the west, or north and south, or left and right, up and down, etc., etc. You pick a direction to be positive, and then the opposite direction will be negative. Okay, so you have to be very careful about direction. Now, almost everyone is very careful right now when we do forces. Okay, we make an axis. We're very good at this point at saying, okay, this force is in the positive direction, this force is in the negative direction. We have to be even more careful here. Okay, once you notice that you're dealing with two different directions, you've got to pick one to be positive, and the other direction will be negative. And any quantities associated with those two directions will either get a positive or a negative sign. Here's our example. An object with a mass of 5 kilograms, so that's m, has an initial velocity of 7 meters per second east, v naught. It experiences an impulse of 15 newton seconds to the west. Notice that we're already talking east and west. What is the object's final velocity? So we're looking for v. We have j, impulse, we have mass, we know the initial velocity, we're looking for the final velocity. So I come up here and I say, okay, which of these terms do I really need? I want to know the final velocity. So that means this delta v is final velocity minus initial velocity. I know I'm going to need this term. I wasn't told anything about the change in momentum. I wasn't told anything about a net force or a time, but I was given an impulse. Instead of writing all this down, I'm only going to pick the parts that are useful, j and m delta v. And I'm going to expand that m delta v to m times v minus v naught. Now it's as simple as plugging in. Although, before I plug in, I do have to make one more notation. I said if you have different directions, you've got to pick one to be positive, the other one will end up being negative. Right now, I'm going to pick east to be positive, which means anything to the west is negative. So as I go to plug in and I say my impulse is 15 newton seconds to the west, Guess what? That's now negative 15 Newton seconds. The mass is 5 kilograms. V is what I'm looking for, minus initial velocity 7 meters per second to the east. It doesn't need an extra negative, I just do minus 7. This becomes negative 15. I'm going to distribute that 5 to both terms, equals 5V minus 35. I add the 35 to the other side, I get 20, divide by 5, I get V equals 4 meters per second. And notice that since my answer is positive, the final velocity must be east. If it had come out to be negative, that would mean it's to the west. So I'm just going to write down, you don't need to do this, but I'm just going to put in parentheses, the 4 meters per second is to the east. And just to show you that it doesn't matter which direction you pick to be positive or negative initially, imagine if I had made west positive. I would have had a positive 15 equals 5 times V minus a negative 7, because then east would have been negative. I would have had 15 equals 5V plus 35. I would have subtracted the 35 to the other side. 15 minus 35 is negative 20. Divide by 5, I would have gotten negative 4 for the velocity. Now you might say, wait a sec, that's different. But if I'm saying west is positive and I get a negative answer, then that means that the answer was really to the east. Okay? The negative just implies east if I'm saying west is positive, and therefore I really have the same answer as I did before. The negative 4 meters per second in that case would have meant 4 meters per second to the east, which is exactly what I got. Okay? You don't have to do it both ways. You pick one direction and you stick with that. Okay? But you do have to pick a direction. You have to remember to do that. Let's go to the back. Mostly some concept stuff on the back. Okay. So, a couple of things that we've got to keep in mind. If the momentum of an object is changing, then what do we know? Okay? If the momentum is changing, we know a few things, okay, other than just momentum is changing. Since momentum is mass times velocity, and the mass doesn't typically change, if the momentum is changing, that tells us that the velocity is changing. And if the velocity of an object is changing, then if we think back to our definition of acceleration, acceleration is a change in velocity over time. If the velocity changes, that means that the object is accelerating. And finally, that also means that if we think back to Newton's second law, the net force on an object is equal to the product of the mass times the acceleration. If the object is accelerating, then that means there must be a net force on the object. In other words, the net force is not 0 newtons. The inverses are also true. If the momentum of an object is not changing, if P is not changing, then neither M nor V can be changing, since M is pretty much always constant. That means the velocity is constant. Doesn't mean it's 0. It could be 0, but it could also be some constant number, like 6 or negative 14. The velocity is constant if the momentum is not changing. Also, if the velocity is constant, that means that there is no acceleration for the object. The object has no acceleration. And also, it means that the net force on the object is 0 newtons. So knowing things about whether the object has a changing momentum or not also lead to these conclusions about the velocity, the acceleration, the velocity of the object, the acceleration of the object, and the net force that's acting on the object. And as a matter of fact, this whole tying everything up together, the momentum and the net force and velocity and acceleration, it actually goes back to Isaac Newton. When Isaac Newton first wrote down in his very famous book, Principia Mathematica, this is where Newton's laws come from. When he first wrote down Newton's second law, he did not write it down the way that we know it today. Originally, Newton wrote this. He wrote that the net force on an object is equal to, this looks like d times p over d times t. If you're in calculus right now, if you're in AP calculus, then you've probably done derivatives and you know what this says. But even if you aren't in calculus, that's fine. I'll give you a real quick rundown of what this means. F net equals dp over dt. What this really means is the change in p being momentum over a change in time. The d's just stand for like really, really small time periods and really, really small changes in momentum. Another way that we could write this, if you're in calculus, you would write d over dt, meaning the change over time in momentum. We know that momentum is m times v. And if you're in calculus, then you know if something doesn't change with respect to a certain variable, basically what we're doing here is we're saying the change over time in m times v. The mass of an object doesn't typically change over time, okay? At least over no time scales that we care about. If something is constant and doesn't change with respect to a certain variable, in other words, mass doesn't change with respect to time, you can move it out front. So we could write this as m times d over dt for v. In other words, the net force is equal to the mass times the change with respect to time of velocity. Say that a couple times, the change with respect to time of velocity. Kind of sounds like the change in velocity over a period of time. Matter of fact, if I move the v up here, then I'd have dv over dt, change in velocity over change in time. We know what that is. Change in velocity over change in time is acceleration. So this thing that Newton wrote down actually turns out to be Newton's second law in its current form, but he wrote it down a little bit differently. So that's just a fun little diversion that I learned about in college. I always thought it was kind of interesting. Newton wrote down Newton's second law, or his second law, in terms of calculus principles. We don't say it like that usually today, but it's essentially equivalent. The last thing I want to talk about in this video is a concept that seems to come up a bunch, and it has to do with how impulse and momentum are related to an object, to two different objects that are being stopped in different ways. So imagine stopping an object of mass m and velocity v with a brick wall. Compare this scenario to stopping the same object moving at the same velocity with a mattress. In which case will the impulse be the highest? In which case will the net force be the highest? In which case will the time that the net force is applied for be the highest? First thing I'm going to do is I'm going to write down that kind of chain of equations, just so we have something to reference. The impulse on an object is equal to the net force on the object multiplied by the time that the net force acts for. It's also equal to the mass of the object multiplied by the change in velocity of the object, which means it's also equal to delta p, the change in momentum. Impulse equals change in momentum, as well as these other expressions. Now, we have an object of mass m and velocity v being stopped by a brick wall. It doesn't matter what object it is. Maybe it's an egg, maybe it's a car, maybe it's a person. Compare this scenario to stopping the same object moving with the same velocity with a mattress. And notice that in both cases we're stopping the object. Stopping implies that the final velocity is going to be 0. So if the final velocity is 0 for both situations, and it's the same object, meaning same mass, moving at the same velocity, implied same initial velocity, then doesn't that mean the product of the mass and the change in velocity is the same each time? It of course does. So if m delta v is always the same for both these scenarios, that means the impulse is the same. So in which case will the impulse be highest? Well, neither. Because there's the same mass and the same delta v. So that's important. Notice that those are the same. If you were to get a question like this, I would write that down immediately. You know that it's the same mass and the same change in velocity because the initial and final velocities are the same. Now, in which case will the net force on the object be the highest? You might be tempted to say, oh, it's the same in both cases, but it's not. And you might be tempted to say that the time that the net force is applied for will be the highest, but it's really not. Let's actually look at the last part first, because that's a little bit easier to see. Imagine an object getting stopped by a brick wall. Brick walls are pretty notoriously hard to break down. An object that gets stopped by a brick wall is not going to do that much to the brick wall. The brick wall is going to bring it to rest very fast. The brick wall is not really going to change just because you, let's say, throw an egg at it or whatever. Let's pretend the object is an egg. Even if you run a car into a brick wall, there's a good chance that the brick wall just kind of stands there. Compare that to a mattress. Okay? A mattress is soft. A mattress can give to it. A mattress will compress or deform when that object hits it. So think about it like this. as that mattress gives way, it allows the object to continue moving. It actually takes a longer period of time for the mattress to stop the object. Compare that to a brick wall. Brick wall is going to stop the object almost immediately. So in which case will the time that the net force is applied for be the highest? The mattress takes more time to bring the object to rest. Now, what does that imply? Okay, so the mattress, the time that the net force is applied for will be the highest with the mattress. We just got done saying that the impulse is the same for both cases. The time is not the same. The mattress will take more time to stop the object. What does that tell you about the net force? If J is the same for both cases and the T's are different, the net forces have to be different as well. And if the time is higher for the mattress, the net force has to be smaller in order to get the same J. If this goes up, then if T goes up, if the time increases, the net force has to decrease so that we still get the same impulse, the same change in momentum. So with the mattress, we actually get a smaller net force. And that kind of makes sense if you think about it. You're just taking a smaller net force and spreading it out over a larger period of time. Let's go back to this question. In which case will the net force on the object be the highest? Well, we've kind of answered that now. The mattress will have a smaller net force because it takes a long period of time to stop the object. The brick wall, on the other hand, takes a very small amount of time to stop the object. It needs a really big net force to cause that change, that acceleration, that change in momentum. So if you want a big force to stop something, that means you're going to stop it very quickly. The brick wall will stop the object will stop, or no, stops in, I just don't like how that word's written, stops in less time. So F net must be bigger. So in this scenario where we have an object with the same mass and same change in velocity stopping with a brick wall and with a mattress, the brick wall will stop it quicker, less time, so the net force must be more. The mattress will stop it in more time, so the net force must be less. Now, that's an example we see a lot. I'm not always going to tell you that the impulse is always the same. You could have something else, or I'm not always going to tell you that the mass and the change in velocity are always going to be the same. You could have a situation where you apply the same net force for the same amount of time to an object. So therefore, again, the impulse is the same, but the objects could have totally different masses and therefore totally different changes in velocity. You could even have situations where you could have situations where the impulses and the changes in momentum themselves aren't the same. You really have to parse through the question and understand what is being told to you, what is the same, what is possibly different, okay? In this case, we were told same object, so same mass, and same final velocity and same initial velocity, so we knew the impulses were the same. In any case, here's our conclusion. If two identical objects are moving at the same initial velocity, but are stopped, I'll put it in quotes, differently, the impulse must be equal for each. However, F net and T can change. A soft stop has a high time but low net force, whereas a hard stop has a low time but a very high net force. And again, that's not the only situation you could see. You could also see a case where the net force and the time are the same, but the mass and the change in velocity are different. The key is to really read your question and see what the question tells you is the same and what is different, okay? But this is a pretty common question type. You'll definitely see this as we go through the units. That's it for the intro for impulse and momentum. There's only one more note video, and it's on a topic called conservation of momentum. Very similar to conservation of energy and just as important.